Good morning, and well, actually, it may not be morning. Who knows what time it is when you're watching this? But welcome to our little video this morning on the mole. And so, what we're going to do today is talk about the mole. And here's a nice picture of a naked mole, right? Let's give him a mustache there. He looks a little better with the bigger mustache. Maybe an earring. I think that's an ear, or just a hole in his head, but that's probably an ear. It's kind of ugly. But so the mole is the fuzzy, cuddly thing in chemistry because there's lots of stupid pictures of moles that you can look at. But mole is actually, it's a Latin term that means massive heap. So we're not really talking about moles. We're talking about a massive heap of atoms or elements or molecules. And let's think about this. So what is a dozen? A dozen is 12, right? You buy cookies in dozens, donuts in dozens. I don't know what else you buy in dozen. You could buy a dozen. Let's see. Dozen roses. There you go. Valentine's Day was just over. I didn't get my wife a dozen donuts. Wait, no. I should have given her a dozen donuts. I didn't give her a dozen roses. A gross. A gross is 144. A gross is a dozen. 12 times 12 is 144. You can buy paper in reams. So one of those cases is 500 sheets. And all these numbers are ways to make counting easier. And in chemistry, we have that, except instead of a dozen or a gross or a ream, we have a mole, which is 6.02 times 10 to the 23rd. And it is a humongous number, all right? So where does this number come from? Well, it is the same number of atoms of carbon 12 and 12 grams of carbon 12. So that's where that number comes from. Everything is based upon the number of atoms in 12 grams of carbon. So here's the definition. It's the amount of pure substance containing the same number of chemical units as there are atoms in exactly 12 grams of carbon 12. So that's nice. Down here you can also see some other moles. This is kind of a public service announcement. In case, if you do sometimes have a mole that you know is growing and you perhaps get an irregular shaped border, or I think it's really black, then maybe you need to have a doctor check out your mole because it could be cancer. So, besides stopping the spread of cancer on your skin, don't go to don't go to tanning salons, things like that. You need to know that one mole is 6.02 times 10 to the 23rd molecules or atoms. That's what we'll think of it mostly in chemistry. It's going to be atoms or molecules. And the other thing is the molar mass, which is the mass of one mole, is numerically equal to the formula mass. And formula mass is what we have been finding, except now, right, and we've been kind of using units of AMU for that. Well, now we're going to be finding molar mass, and we're going to be using units of grams. It's calculated the exact same way as before. Now, this is sometimes called Avogadro's number. It's named after Amadeo Avogadro. He's kind of a scary looking guy. He didn't discover it. It's just named after him. He was originally involved in finding some atomic weights of elements, I believe. Here's just another, oh look, it's another cute mole, right? Can't even see his eyes. There's his eyes. Now he looks better, right? Maybe he's got glasses on. I think in some cartoon moles have glasses on. All right. So, how big is a mole? Well, could you count to one mole if you counted one number per second for the rest of your life? So let's say you lived 80 years. There's 365 days in a year. There's 24 hours in the day. There's 60 minutes in an hour. There's 60 seconds in a minute. And let's say you came out, bam. Doctor, this baby started counting. It's a miracle, right? So let's say you counted from birth all the way for 80 years. You would still only get to 2.52 times 10 to the 9th. So that's not even close. Well, what if everybody in the world counted with you? Well, theoretically, I think now, although this is probably off, this was when the population was roughly 7.1 billion. So let's say every 7.1 billion people counted for 80 years. you still wouldn't make it. You would still be 10,000 times smaller than what a mole is. So a mole is a giant number. And then there's an investigation on page 39 that we can look at, but that's not for your notes. So we'll skip this. If you're in class, we'll probably do this in class. Otherwise, you can look at it and give that a try. Oh, it's thinking. All right, so there's that. All right, so let's go back to this. So you need to remember that the molar mass is the mass of one mole, and that is equal to the formula mass, numerically equal to the formula mass. Formula mass is in AMUs, mass of one mole is in grams. So the molar mass of any element is numerically equal to its atomic mass in grams. So the molar mass of gold. So you look on your periodic table, what's the mass of gold? It's 196.97, and we're just going to call that grams. So the molar mass of gold is 196.97 grams. So that means that if you had 196.97 grams of gold, you would have 6.022 times 10 to the 23rd atoms of gold. So let's look up helium, and let's look up, this is titanium, it's not TL, it's not tantalum. So helium is 4.00 grams. Titanium is 47.88 grams, and you get that directly from your periodic table. Now, for an ionic or covalent compound, the molar mass is equal to the formula mass, numerically equal to the formula mass. So let's look at the molar mass of water. So we have 2 hydrogens, 1 oxygen, hydrogen's roughly 1.01, oxygen 16.00, so we get 18.02. So the molar mass of water is 18.02 grams. Now, we're going to go back to the T-chart method, and we did this when we were doing metric conversions, and now we're going to do it for these mole calculations. So these are the steps. If you will read these steps and go through this and follow the directions, you will be able to do this. Many of you will refuse to look at this. I know this because it happens every year. You refuse to look at this, you won't read it, and you'll say to me, I don't know how to do this. And I'll say, did you read step 1? And you'll say no, and you'll read it. I said, did you read step 2? No, and you'll read it. Did you read step 3 and do what it says? No. So let's try to cut that out and read these directions and do the problems. Now, we'll go through some examples of how to do this, and I think it'll make sense, and then you can just use this as a reference. But it's exactly what we did with metric conversions. Then the other thing is you need to fill in this chart. Sorry, I had to get a swig of coffee there. You need to fill in this chart in your notes. This is our game plan. This is what you need to know. This is like what you need to get tattooed on your forearm so you can look at it during a test or written on the bottom of your shoe or something like that. You need to have this memorized. You should go to sleep, you should see this. You wake up, you see this, right? You squeeze some ketchup out for your French fries. Somehow you should see this in the writing of the ketchup. So write this down, memorize it, sleep on it, whatever you need to do. This is our game plan. And the thing about this is you can go directly from moles to grams. You can go directly from moles to the number of molecules or atoms. But if you want to go from grams to molecules or atoms, everything has to go through moles. All right, and we'll look at some problems that do that. So here is, all right, before we get to that, sorry, I thought we had a problem here. To convert between moles and grams of a substance, you have to know the molar mass of the substance. So remember, the molar mass is just the formula mass. So here's our first problem. Find the number of atoms in 3 moles of lead. All right, so where are we starting with? Well, we're starting with 3 moles of lead. So we're starting in this box. And remember, we want to find this box's number. So we want to go from moles to number of atoms. All right? So we follow the T-chart method. First thing you do is you make your T-chart. All right? Then whatever you start with, whatever you're given, which in this case is 3 moles of lead, whatever you're given goes in the upper left right here. So we put 3 moles of lead in the upper left. And the abbreviation for moles, and I don't think I've said this yet, is MOL. So it doesn't save you a lot of time. It saves you like, let's see, moles has 1, 2, 3, 5 letters, so you knock off 2, so that's like 40%. Save you 40% time. Now, whatever you start with here, that unit goes here. So if we start with moles of lead in the upper right, moles of lead goes in the bottom right. What you want to find always goes in the top right, and we want to find the number of atoms of lead. So atoms, and this should really say atoms of lead, and let's extend this line here, goes in the top. So what is the relationship? What do we know? How do we go from moles to number of atoms? What do we know? Well, whenever you have moles on your conversion side, for now, we're always going to put a 1 in front of the mole, because in 1 mole of lead, how many atoms are there? 1 mole of anything, we know there are 6.022 times 10 to the 23rd atoms. All right, so we set up our T-chart. And then remember, to solve this, we take 3 moles of lead times 6.022 times 10 to the 23rd atoms divided by 1 mole of lead. And you see moles of lead cancels out, right? These units cancel out. And so what we're left is 3 times 6.02 times 10 to the 23rd atoms. And we end up with 2 times 10 to the 24th atoms of lead. Now remember, to put scientific notation into your calculators, you probably need to use the E buttons. And we have a video on that if you need help, or you can ask me in class. So that's our first type of problem. We went from moles to number of atoms. All right, second problem here. Find the moles of beryllium and 4.8 times 10 to the 45 atoms of beryllium. So once again, first thing you do is you make your T-chart. Now, here, right, we're starting with 4.8 times 10 to the 45 atoms of beryllium, and we want to find moles. So this time, we're going from this box to this box. And once again, to do that, we need to use Avogadro's number, because we know 1 mole is 6.02 times 10 to the 23rd. So if we start with, this is what we're given. So this will go where? This will go in the top left box. So 4.8 times 10 to the 45 atoms of beryllium. If we start with atoms of beryllium, this unit is going to go down here. Oops, that's kind of messed up. So atoms of beryllium goes down here, and then we want to find moles, so moles goes in the top right. All right, once again, moles to atoms. On this right side, which are our conversion side, we want to put a 1 in front of the moles, because in 1 mole, how many atoms are there? Well, there's 6.022 times 10 to the 23rd. So we multiply the top 2 numbers, divide by the bottom. All right, this is our setup. And then remember, once again, atoms of beryllium will cancel out, so we're left with moles of beryllium. So we have 4.8 times 10 to the 45 divided by 6.022 times 10 to the 23rd. We get 8.0 times 10 to the 21 moles of beryllium, give or take a few million. All right, third example problem. Now, this time, what are we starting with? We have 345 grams of calcium hydroxide. All right, now, we want to find moles. So we want to go from here, this box, to this box. To do that, we're going to have to find the molar mass. So the first thing you need to do is you need to find the molar mass of calcium hydroxide. Or in this case, I made the T-chart. So we're starting with 345 grams of calcium hydroxide. So grams of calcium hydroxide goes on the bottom right. Moles of calcium hydroxide goes on the top right. All right. Moles to grams. We always want to put a 1 in front of the moles of calcium hydroxide because we know in 1 mole we can figure out how many grams there are. So you got to add this up. We've got 1 calcium, which is 40 something, 2 oxygens times 16, 2 hydrogens times 1.0079. You add all that up and bam, 74.10 grams of calcium hydroxide. Just like before, multiply the top numbers, divide by the bottom, and you should get 4.66 moles of calcium hydroxide. And remember, the grams of calcium hydroxide cancel out. We're left with moles of calcium hydroxide. All right, final problem. Find the number of grams in 0.588 moles of ammonium bromide. All right, so now we're starting here, and we want to go here. So once again, we're still going to need to use molar mass. So we make our T-chart. 0.558 moles of ammonium bromide. So ammonium bromide goes in the bottom right. Grams goes in the top. And I really should have a label here. This should be just to be correct. All right, what are we going to put in front of the moles? We're going to put 1 in front of moles because that's the molar mass. And then we look at the formula. We have 1 nitrogen times 14, 4 hydrogens times 1, roughly 1 bromine times 79.90. Add all that up, you get 97.95 grams. That's the molar mass of ammonium bromide. So multiply the top 2 numbers, divide by the bottom, you should get 54.6 grams of ammonium bromide. So we did moles to grams, we did grams to moles, we did a moles to number of atoms, molecules, and we did this. So really we did what I would say template problems for each of these. So if you need help, any questions, come ask me in class or before or after school or during lunch. All right, goodbye. Hope you enjoyed this video.